She was almost going to give me a 0 on the test. Snow day, because I didn't go yesterday. So I was like super upset I didn't get it.
Should we go early?
And she literally almost gave me a 0. I was like, are you fucking kidding me?
All right. I wanted to start where we left off. And we left off talking about this process of reabsorption. And we're gonna talk about glucose as an example of this because a couple of reasons. Glucose reabsorption is obviously really important, but it's also something that's affected in a way through diabetes. The diabetes is something we'll spend a little bit of time talking about later on in the semester. But one of the things that characterizes diabetes is the presence of glucose in the urine. In fact, that's the way it was originally diagnosed, is by tasting the urine. Great idea, right? And finding out that there's glucose there. There should be absolutely no glucose in your urine if you have a normal glucose metabolism in your body. So how do we reabsorb this glucose? We went through the mechanism last time, and we had a pull everywhere result that indicated to me that I wanted to spend just a moment talking about this before we move on to looking at the graph that describes this, which is a little bit more complicated. So we have, let's say 100 milligrams per deciliter. That's the typical way of measuring glucose. A deciliter is, what is a deciliter? What's a deciliter? Tenth of a liter, right? So it's 100 milliliters. Don't know why, but that's the standard. Okay, 100 the units don't really matter, but 100. Okay, and we end up with, so we have 100 milliliters per deciliter in the blood. Okay, and as we pass that blood through the glomerular capillaries, that blood plasma, about a fifth of it, passes out of the blood into the tubule. Okay, and when we say a fifth of it, we're talking about the volume, right? A fifth of the volume over time, which means that we have the same concentration in the blood as we do in the tubular fluid here on the far left. Okay, and that's true of all of the things that we filter. Okay, so if sodium is 150 millimole concentration in the blood, that's going to be the same concentration in the tubular fluid, the filtrate, here on the far left. Okay, so the concentration of everything stays the same as filtration takes place. Okay, the exception being proteins. Proteins are not going to change, and they make up a small amount, so they don't affect the total much. Okay. All right, so now we've got tubular fluid here in the yellow passing down through our nephron. Okay, the proximal tubule in particular is an area where we do lots and lots of glucose reabsorption. Okay. So the first thing we talked about last time is that we're going to use active transport, and we're going to develop a very strong, or maintain at least, a very strong intracellular sodium concentrate, or very strongly low, is that, can I say that? Strongly low? A very, very low concentration of sodium inside the cell, right? Very little sodium in the cell because of active transport. Now, what that means is that we get a very strong activity here, driven by sodium, that pulls not only sodium into the cell, but also glucose. Okay. And what will happen over time is that 100 milligrams per DL in the tubular fluid will go down to 0. And we will continually pump glucose into those cells of the tubule. Okay, so the cells that make up the tubular wall are going to have the highest concentration of glucose of places in the body. Okay, we have very high glucose levels. Okay, and then from there, right, so let's say draw a little arrow here to represent that we've really increased this value and decreased this value. And then from here, all the way to the blood, every movement of glucose is going to be through passive mechanisms. Okay, so it's going to go through this GLUT transporter. Okay, this is a facilitated diffusion transporter. meaning that it could go both ways, but what's going to happen is that owing to the concentration that we're creating through secondary active transport, glucose is going to move in this direction, okay? Right, which means this value is going to be a little bit higher, maybe not as high as what was in the cells, but it's going to be a little bit higher, right? So, what happens? Glucose goes from tubular fluid to the cells to the interstitial fluid, and from there, it's going to pass into the blood plasma. Okay? So it's just a series of downhill or down concentration gradient movements of glucose from the tubular cells back into the blood. Okay. And as long as you're not diabetic, this level on the far left will be low enough to start with that we can move all of it. Okay. And with diabetes, whether type 1 or type 2, that number gets really high. If we have hyperglycemia, then we get to the point where we can no longer transport all of it. Okay? But even if that's the case, we still develop this strong gradient for reabsorption from the cells over to the blood. Okay. So the question that we ended with last time was, which of these spaces has the highest concentration of glucose? And the answer was what? Inside those tubular cells. Yeah. Any questions about this process? What we'll see later on is that reabsorption of a lot of things works through exactly the same types of movements. Okay? We may not have sodium glucose transporters and passive diffusion transporters to move an amino acid, right? But we'll have an amino acid sodium transporter in the place of what we see here. And then we'll have passive diffusion. So the setup is very, very similar for most things that we're going to reabsorb. Okay, so if you learn glucose, you'll learn what's also true of a lot of other types of substances. Okay, so let's move on then. We have glucose reabsorption, and we're going to talk about a couple of concepts here. So one is the filtered load. And I know in your reading, and something we'll get to in a little bit, is this idea of clearance, which is kind of a weird concept. I think this one is a similar concept. It's a little bit more intuitive, or a little bit more understandable. Okay? So filtered load. Right? What do we mean when we say the filtered load of glucose? Let's put it in plain terms. What does it mean to have a filtered load of glucose? What are we asking? How much? What? Yeah.
How much
Right. How much glucose, or in milligrams, is going to be filtered at glomerulus, or all of the glomeruli together, right? The whole filtration membrane. Okay. So, how much that is? Well, that number will depend upon how much is in the blood. Okay. And you can see very clearly there's a more or less one-to-one relationship. Right? If we have the number we talked about, a normal plasma glucose level of 100, how much is going to be filtered? 100. Okay. If we have 500, that's huge. 500 milligrams of glucose. Right? Maybe my chart needs adjusting. I'm drawing airplanes. It should be 1-to-1. My line is a little bit off, but you get the idea. There's a linear relationship here. As much glucose as in the blood is going to be filtered. Okay? So a filtered load just simply means how much of that substance gets put into that tubular fluid inside of our nephrons. Okay? So that's the filtered load. Okay? And seemingly there's no limit to it, right? There's no limit here. Perfectly fine. That filtration membrane can handle whatever we throw at it. Okay. So filtration is linearly proportional to the glucose concentration in the blood plasma. Okay. Now we get to reabsorption. This line looks thin. So up until about 200 milligrams of plasma glucose, what can we say?
It's linear.
Also proportional. Okay, so we can filter 200 milligrams per deciliter, okay? And every one of those milligrams of glucose, every one of those glucose molecules will get reabsorbed back, okay? Proportional relationship. So we can dump X amount of glucose into the filtrate and we reabsorb exactly that much back, okay? No problem. But what happens when we get higher here? 300, you see that curve start to bend. And 400 and beyond, what happens to reabsorption? What's happened to reabsorption? It hasn't stopped, but what's happened? It's leveled off. It's reached a maximum. We call this the transport maximum. You'll see this as T sub M, transport maximum. What does that mean? It means that we after about 400 milligrams per deciliter, any more filtered glucose will not be reabsorbed. Okay. So we can reabsorb every bit of 200, but once we get above that, we start to taper off and reach this level. And by 400 and higher milligrams that end up in the plasma, end up in the filtrate, we are unable to reclaim that proportional reabsorption, right? Okay. So, if your blood, you wouldn't have this level, but if you had a blood glucose level of 500, how much would you reabsorb? 200, okay? If it was 1,000, 200, that's all you can reabsorb, okay? And the reason for that has to do with these transporters, right? I drew one, obviously, or one pair of transporters here, but there's thousands of these on each cell, okay? And these are found throughout the proximal tubule, but then nowhere else in the nephron, okay? So there's a segment of the nephron where that tubular fluid's passing through, and we can deplete all of the glucose from that volume, so long as the concentration isn't higher than 200, okay? So we have a maximum. We can only move so many molecules. Yeah?
You said the maximum is 200 or 400?
So the maximum is considered 200. And the reason that we get this sort of tapering curve, it kind of comes down to semantics. For our purposes, we'll say the maximum is 200 because this is the point where that linear nature of things cuts off. But there is a change over a range of concentrations that has to do with the more nuance to how this works, right? So in actuality, you might have some open transporters, but those glucose molecules might bounce off of them, right? And all this kind of stuff has to do with binding affinities and all that sort of thing. Well, it turns out these transporters have kind of a low affinity. And if they bounce off one of the transporters, that's okay, they'll get picked up by one further down. But once you get over 200, you're running out of available transporters. Okay, so we say 200 is the max, but in actuality, it just has to do with that's sort of the end of our ability to reclaim 100%. Okay, but you can see here at 400 and above, there's no chance of reabsorbing anymore. I wouldn't concern yourself with that, but it is a real thing. That area of the curve is called splay. And you could read articles and articles about it. Really fascinating stuff. Online. Okay, so reabsorption, or this is going to be equivalent to the filtered load in this linear fashion up until 200. Okay. Then we get to RTM. So what does this tell you about excretion? Well, we could draw a line for that too. Okay. So in other words, how much do we get rid of, right? How much of the glucose that's in the blood plasma do we get rid of? Well, up until 200, how much do we get rid of?
3 grams.
Nothing, right? We don't get rid of any of it. Why not? It's all reabsorbed, okay? So up until 200, we're dumping all that glucose into the filtrate, but we are able to reabsorb all of it, and we excrete none of it, okay? So if you don't have diabetes, you should not have any glucose in your urine, not at all, okay? But as you get past 200, it starts to appear, okay? And once we get past this level of about 400, where we have that little gray area, right? Any more that you filter is going to also be excreted, okay? So we only have this capacity to reabsorb so much. Anything else that's not reabsorbed gets excreted, okay? Now, in principle, let me put this out here. In principle, every substance that we're reabsorbing should have a transport maximum, right? Because all of these transporters can become saturated. Right? Typically, there's not any problems associated with other types of transport maximums being reached, okay? But it's something that we can use clinically to observe diabetes, right? So in diabetes, we have blood tests, right? But urine tests are also quite easy to do, and you can, if somebody's got urine, it's a quick and easy, urine with glucose, it's a quick and easy way to know that they've got a glucose problem, okay? But you can have the same for amino acids or whatever, in theory. All right, any questions about, the most important thing to me is that you understand what's happening here. But I do want you to understand the sort of repercussions of this in terms of we filter proportionally to what's in the blood plasma, and we reabsorb proportionally to what's filtered to a point. Okay. And anything that's not reabsorbed, of course, we excrete. Any questions on this material? Yeah.
What if there's really high pressure in the tube? Like, what if you drank a few gallon or two of water? Like, could you still reabsorb like that?
That's a great question. So this is assuming a constant and normal GFR. Okay, so if you had something that altered your filtration rate, you would guess that fluid is moving rapidly, right? And you would have an inability to reabsorb as much as normal. And that's that principle we talked about before, that reabsorption depends upon consistent GFR. So, yeah, it would be affected. I could ask you a test question about this to help assess whether you understand the directionality of that, right? So let's say you had a high GFR, right? You drank a couple gallons of water, right? And if you drank a couple gallons of water, you have high GFR, right? And what impact would that have on glucose levels? Would you expect to reabsorb more or less? And you should all say less, right? And the reason is that if that filtrate is moving quickly, you have a decreased capacity to reabsorb those molecules. In other words, they're flying by too quickly to reabsorb. Yeah.
So if a normal, like, healthy person just ate a lot of sugar, are they more, like, will they just store that in as fat instead of excreting it?
So without getting too far into diabetes, which we'll do later, if she asked if we ingest a lot of sugar, the normal response to sugar being found in the blood is that we release insulin, which helps us to pull the glucose into our cells. Okay, and that's the normal response, not because glucose is bad, but because we need those molecules. That's energy. Okay, so if we have a problem with that insulin response, that's when we have a situation like this, where instead of keeping our glucose under 100, it can go up to 2 or 3 or 400, because insulin is not properly causing cells to pull that sugar in. Yeah, and yeah, when cells pull glucose in, we use it for lots of things. We can use it in glycolysis, right, for energy right away. We can use it to make fats, right? It's called lipogenesis. We have a surplus of glucose, we turn that into fat for later use. We can store it as glycogen. Remember these things? Maybe glycogen as storage form of glucose. You can do lots of things with it. Yeah, but our bodies like glucose. It's good. It's good stuff, right? We build things out of it or break it down for energy. Okay, we will spend some time talking about diabetes later on, near the end of the course. Okay, so briefly, and then we'll get on to some other material. Briefly, we're going to talk about secretion. Reabsorption is a very big event, right? And lots of things get reabsorbed, put back into the blood. Secretion takes things out of the blood and puts them into tubular fluid that's passing on its way to become urine. There's far fewer things that we put into the filtrate. And this would probably make sense, right? Because filtration puts things into the filtrate, right? So we already have a process that puts things in to the filtrate to become urine. Okay. So why do we need this extra process? Well, this is a way that we can fine-tune a couple of important things. The two major things you should be aware of that we secrete are hydrogen ions and potassium. Okay. Hydrogen ions and potassium. These are two things we sort of fine-tune, and it tends to be at the end of the nephron, so collecting duct and the distal tubule, mostly. Okay. All right, what does that process look like? It's pretty much the same thing. We're moving substances from the blood into the tubular fluid. The way that it works generally is that we will have some type of transporter on either side of the cell, okay? And we can move substances like this from the cells into the lumen, right? And thereby pull through diffusion processes those elements out of the blood to replace them, okay? So this is how we do it with potassium, with hydrogen ions, okay? And the only difference is where is the active component, whether it's on the apical or basolateral side. It doesn't really matter right here, right now, okay? But basically we're pulling things out of the blood by having processes that drive either hydrogen or potassium into the lumen, okay? Okay, so in terms of hydrogen, this is the way that we have of regulating pH. It's a very important process, making some fine-tune adjustments to our blood pH. Okay. The last thing I want to show you here before we get on to the topic of clearance is there are divisions of our nephron, as we labeled them last time. And there's lots of things moving around here. Okay? And we are going to talk about some of these things, not all of them. But I want you to begin to think about these in categories more so than individual things, and that'll make it a little bit easier. Okay? So, maybe you don't know what all of these things are, but you could put all of these things in the category of glucose, as these are things that we filter because they're small molecules, but we need them, right? And we pull them all back into the blood, okay? So we might call these nutrients, okay? Glucose, amino acids. There is urea here, which is a waste product, but generally we're in the proximal tubule, we're pulling stuff out to put back in the blood. Okay. We also reabsorb a huge number of ions in water. Okay. This proximal tubule, and then we'll move on. Proximal tubule is probably the most important part of the nephron when it comes to making sure that we don't deplete our body's source of ions and water and nutrients. Okay, so it's really, really important. The amount of the total that's filtered that we reabsorb here is about 2/3. Okay. So that whole nephron, right? We've got that whole nephron to reabsorb water and sodium and all these kinds of things. But we do 2/3 of it in just this first segment, proximal tubule. these things, it's more in the range of 100 in the case of glucose. So maybe 50 in the case of urea. But when it comes to glucose and amino acids, we want all of that back. Okay? And then the rest of this, there's a lot of fine tuning that takes place, but we are reabsorbing a tremendous amount of things in that proximal tubule. Okay? And then secretion, just to reiterate what I said earlier. What are we secreting? Hydrogen, potassium, hydrogen, right? We don't secrete much, very little. Okay, reabsorption is where it's at. So what we're going to do is we're going to talk about some bigger picture processes with regard to the kidneys, and then later on we'll spend some time talking about some of these specific substances and how we do things. Okay. All right. So. Somebody found this topic a little bit weird or confusing or not intuitive when you encountered it with the renal clearance. Just me? Okay. I always thought this was weird. Maybe it's just me. All right, so we have this idea of a filtered load. You remember that? And we said a filtered load is how much of a substance is leaving the blood plasma and enters the filtrate. Okay. And we have an excreted load, which tells us how much of that substance that's in the blood plasma ends up in the urine. Okay. So if we're thinking about the individual substances and how much of them, how many milligrams, the filtered load, the excreted load, these are pretty clear ways to think about things. Renal clearance is about the amount of plasma that is completely cleared of a substance in a unit of time. Okay, so urea is a waste product. Okay, and if we're taking blood plasma that's coming in through the arterial side, and it's going through the nephrons and being reabsorbed and all this sort of thing, right? And then that blood enters the venous side, right? Renal veins. And if we put in a liter of blood and we get a liter of blood plasma, and we put we've got a liter of blood plasma coming out, what clearance tells us is how much of that volume has been completely depleted of our substance of interest, in this case urea. Okay? Which is weird because we don't deplete just a little band of it like this, right? We take some out of the total. But what clearance tells us, if we've got this certain volume, right, how much has zero and how much has whatever's normal. Okay? So it's kind of an odd way of thinking about things. In order to calculate this, yes, we have an equation. And I want to spend a moment talking about this. We have an equation that helps us determine the clearance of a particular substance. So clearance of X, we could say urea. What do we need to know in order to figure this out? We need the concentration of X in the plasma. Okay, so how much urea is in the plasma? How many milligrams per whatever? Okay. And then we need to know how much ends up in the urine, right? We've taken that substance and we've got two ways of dealing with that substance that come into the kidney, right? What are the two ways? We could put some of it in the urine, and what else about the rest of it? Where can it go? Back into the blood, right? So substances that enter the kidney will either exit the kidney as urine, or they'll exit as venous blood. Okay? So if we know the concentration in the plasma, and we know how much is in the urine and the volume of urine that's produced, we can calculate how much of that substance has left the blood. Okay? And what we're doing, we're not looking for specifically the amount of the substance, but we're looking for the amount of the plasma cleared of that substance. Okay? So why is this useful? Well, this can tell us something about the rate of cleaning the blood, right? That's a good way of thinking about it. We're cleaning the blood, that's the job of the kidneys. We're getting stuff out of the blood, getting rid of waste products. And we want to know how many milliliters of our blood plasma are getting cleaned, right? That's the way to think properly about renal clearance, okay? But we've got to know how much is in the plasma to begin with, and we have to know how much we're getting rid of, okay? So if we know what's in the, just to illustrate this, if we know what's in here, right, and we know what's coming out here, we can determine what we've cleared, right, over here. Conceptually, you have any questions? Yeah.
So what does dialysis do?
What does dialysis do? Dialysis clears your plasma. Dialysis is a way of removing substances from your blood plasma. Okay, and if somebody has, if they're on dialysis, it's usually because their kidneys aren't functioning properly, right? And need to be able to remove waste products from the blood. Right? And so dialysis will take a couple of different ways, but the most common way of doing dialysis, at least in this country, is to take blood from somebody, pass it through a dialysis filter, and send that blood back. It's been cleaned up, so to speak, back into the circulation. You can't take all the blood out at once, right? That's sort of the downside of this. So you kind of have to do it constantly, right? And that's what your kidneys do. They constantly clear plasma, right? But as soon as that plasma is on its way out of the kidneys, it's mixing with other blood, right? So we have to continually do this process, either with dialysis or with the kidneys. Okay, so let's see if we can do this. We've got, oh, here's my concentration. The B with a little dot is the volume rate, okay, the rate of urine production. Okay, so for a substance that is filtered, right, filtered at the glomerular capillaries, but it's neither secreted nor reabsorbed, it's only filtered. The maximum clearance we could achieve would be what? Equivalent to what value that we've learned about? Okay, so a substance that's filtered, but we're doing nothing else to it. What is that? What's the maximum volume plasma we could possibly